and thanks for the introduction. So I thought I would actually start out this presentation with a history of an inverter participation. A lot of people don't know this, but grid-tied, let's get rid of this lyrics. Grid-tied distributed inverters, so DERs, are actually not that old. It really wasn't until about the year 2000 that you all actually formalized the standard for grid intertied PV, even though people were experimenting them a little bit before that. And back then, the system was so sparse in terms of how many of these resources were actually connected. They were thought of as like basically toys. There's so few PV inverters connected to the grid. The utilities really took a non-participation route where they just wanted inverters to get out of the way. They said, if anything goes wrong with the grid, you shut down, let me take care of it and do my job. I don't want you really doing anything. And that was seen as the safest way to allow PV penetration in the grid without it interfering with any of the actual fundamental controls. But the problem was in sort of the early 2000s, PV costs started to reduce dramatically to the point where it's becoming much more economic to install. And it was starting to cause problems on certain circuits where electricity prices are really high, in particular Hawaii. So Hawaii electricity costs are pretty much the highest they are anywhere in the country. PV was a very popular technology to try to reduce those costs. And we started seeing actual issues crop up on distribution feeders. And this is an actual data capture we took of on Hawaii of over voltage events occurring on the feeder. You can start to see them popping up pretty frequently due to just the high penetration of PV. So the utility started to rethink the strategy, and they really urgently tried to push for some standards to formalize a participatory response. And this is when the smart inverter was born. So they created some governing responses like frequency watt. Probably most importantly, they formalized a ride through, which allowed inverters to remain connected in the event there were disturbances to the grid. And you can see with IEEE 1547 Amendment A and UL 1741 Supplement A, they did a really quick churn to make sure that inverters were even allowed to have these functions to solve some of these problems. And this is starting to get more formalized nowadays. Now, this is actually a little bit out of date, but we're formalizing this with IEEE 1547. So we actually have an official participation model. So what's the problem? Why are we here today? Why is UNIFI forming? We already have these frequency watt volt var functions and ride-throughs. The problem is that these functions actually can't be guaranteed to form a stable grid. And they are overly complicated. So back in the early 1900s, when they were first starting to develop interconnected power system theory, they really required a fundamental approach because they were limited by the technologies of their day, right? They didn't have they didn't have real modern computers like we do. They didn't have advanced digital controls. They only had primitive communication technologies. So that required them to develop a fundamental approach to a solution. So they developed actually some brilliant concepts to do that. 100 years later, we have much better tools available. And this has actually been, in a way, a sort of handicap, in my opinion, because it enabled an overly complicated approach. And that complicated approach, actually, one of my favorite reactions was at the Lower Inertial Microgrids conference a few years ago that Brian put on at University of Washington, when a protection relay engineer from SCL said how much he hated inverters because they're digitally controlled. And he was reliant on these firmware engineers implementing controls correctly. And there aren't firmware bugs in iron and copper. Iron copper performs the way you expect it to perform every single time. And it's easy for him to design protections based on that. Now that we have these microprocessors, we're really vulnerable to bugs that didn't exist before because the approaches are so complicated. So here's a sort of summary of the top 5 issues that I see with the approaches we have right now. There's too many configuration options. And when you have too many configuration options in your functions, it's very difficult for people to validate every possible setting because you create these trees, these configuration trees where settings depend on each other. So validation becomes very challenging, and which is why bugs in software can proliferate into the field, because a lot of times the function's only verified with one setting, and an overflow error or some other nuanced bug can only occur with the different combinations of settings. So validation becomes very challenging. 2, there's no methodologies attached to the functions or the function options. like I mentioned, I'm in weekly meetings where microgrid developers are putting together these RFPs, and they're looking for feedback from inverter manufacturers on, okay, what are the capabilities of the inverter? How should the inverters be programmed? And there doesn't seem to be a great methodology on what are the best functions to activate and when. And even when you know which function you're going to activate, what's the best setting for them? It's it's a lot of trial and error. And there doesn't seem to be a good methodical approach for how do you use all these advanced inverter functions. 3, there's very sparse modeling support. And this is a problem that Brian has been focusing on, has been publishing some stuff on recently, is how do we actually create a modeling framework for these inverters so that they can be verified and simulated, and we know that, okay, they are going to work when they're actually installed. And this is a bit of a chicken and egg problem because, a lot of times the modeling depends on the inverter manufacturers providing models for inverters, but the inverter manufacturers are reluctant to reveal too much detail about how their inverters function, especially with grid forming technology, because they're worried they're going to give away some IP. And then once you have an ability to generate models, how do you actually support generation of that model with all the different configuration settings, right? So the model will actually change depending on how it's configured. 4, functions are not generalized. A lot of functions are very specific to the type of resource that you have, which means that there's a lot of reinventing of the wheel and some confusion about how to model these things depending on the type of resource they're applied to. And then lastly, there's no unified certification process. And this is really creating, I think, a headache for inverter manufacturers because we'll develop a lot of source code and tools to comply with 1547. But then when it comes time to actually being used in a microgrid project, a lot of times there's other functions and features that these manufacturers or these operators and microgrid designers want that aren't part of that standard. And there's no certification process for these custom projects. We can comply to 1547, but in our experience, a lot of times these people want a lot more. And we can do our best to try to provide those with custom firmware builds, but that's a lot of work. And it's difficult to go through. There is no formalized verification process if they're asking for a custom function. So an example of this, I think, would be the SUNSPEC parameterized frequency watt function, which I have shown here. I took this from the SUNSPEC description of the AGF function. This is an example of something I think that was overly complex. So the idea is that you have a certain frequency that the inverter provides a governing response. So it really provides a deadband where the inverter is not providing any response at all. And the idea is that it only reduces power, and it takes a snapshot of its power at its minimum amount, and will hold that power all the way back to the frequency comes back to its original level. This is actually surprisingly difficult to code correctly in firmware. And it's not clear what the value of this hysteresis is. I think this is a lot of legacy from the inverters having no participation. If something goes wrong, get out of the way. Really, this is sort of half and half, right? Where if there's an emergency and the frequency is increasing, I want you to have a governing response. But as soon as you prevent that emergency and you stop this runaway increase in frequency, I don't want you to do anything after that. I want you to hold what your current value is, stop doing anything, and just ramp back up slowly once I'm done. And then lastly, it has some actual undefined behaviors. What exactly do you do if the frequency increases again before this hysteresis loop has completed? So here I think is an example of something that was like overly complicated. It doesn't have a good methodology attached to it. It's challenging to implement and validate. So in my mind, some basic requirements of a new system, functionalities should be generic, which means that they shouldn't be affected by the topology that an inverter manufacturer chooses, or even the resource type that it's attached to, PV, fuel cell, batteries. I think these functions should work on all of them. Functions should be as simple as possible. We want to minimize the configuration trees that fall out of these functions so that they're much easier to validate, and there's basically a scope defined around the different types of models that can be generated. 3, and I think this is actually probably the most important one, every function that we have should have an accompanying methodology for how they should be used. A concrete, concise design process for using control-based physics, saying this function solves this problem and here's how it should be configured. And lastly, is a common format for both configuring inverters as well as generating the models. We should use the same file, the exact same file to configure an inverter and generate a model of that inverter to make sure that it's consistent with how that inverter is configured. Like I said, models are useless if they're wrong, right? So if we don't have a common framework for both configuring the inverter and modeling the inverter, it's going to be very common for human error to cause a microgrid designer to use a model that doesn't actually match the inverter that they're using, or the configuration of the inverter that they're using. So here is my proposal for a simplified, unified model based off of what the problem you're actually trying to solve, tied to device physics. And really, it's going back to the roots, I think, of control. And it's, in my opinion, just a generalized version of the timeline bias controls that are used today. So this is what, in my mind, that function looks like. It's a phasor response that defines the relationship between voltage, frequency, active, and reactive currents. There's a matrix, which I call G, which stands for governing. That's the governing matrix of your system. And that dictates the primary response of these inverters. You have a bias injection, which is in units of basically units of hertz, units of volts for implementing the secondary control biases. And lastly, you have a tertiary bias, which is in units of active amps and reactive amps. And a time constant tau, which sets the speed at which this relationship is enforced. So really, it's just a relationship between voltage, frequency, active, reactive currents. It doesn't specify how that relationship is actually generated. So this could be done with a synchro inverter type of control. This could be done with a classic droop controller that uses a PLL. This could be done with a virtual oscillator control. It could be done with a number of different controls as long as there's a linear relationship that's defined, or even pseudo-linear, where we can kind of linearize the matrix G around the operating point the inverter is currently at. Relationship between voltage, frequency, active, reactive currents. And then a time constant, which will be used to control the phasor dynamics of the system. And here I actually took this scope shot this morning just to kind of show an example. This is what our time constant looks like when you have it basically set to 11, the highest speed that it can possibly operate at. And you can see with advanced DSP on microcontrollers that are not that expensive, you can actually get a very fast response. There's a three-phase equivalent for this, where you run them separately on the positive sequences and the negative sequences. So you can imagine that if you had a three-phase inverter or a system of single-phase inverters, you may want to use sequence decomposition to control both the active reactive currents on both the positive and negative sequences, so that you can do things like phase balancing or negative sequence voltage regulation on your network. So that's the phase modeling. So that really defines the relationship between active, reactive current, and voltage and frequency. But that's all phasor modeling. Those things only have a valid definition averaged over a line cycle. But what about the subcycle characteristics of the inverter? And here's where I think we could develop a framework for doing Thévenin modeling of inverters. How does it look like subcycle? And in which case the inverter manufacturers can provide an equivalent circuit which shows a small signal Thévenin model of what the inverter actually looks like. And an accompanying Bode plot that says how accurate that model is. So, you know, the solid line shown here is a Bode plot of this equivalent circuit on the left. And the dots represent an actual measurement of the small signal characteristics of our IQ8 inverter with a specific configuration setting. Obviously, it look, you know, we emulate these impedances digitally, so it'll look different under different settings. But the nice thing about this is it shows how accurate, to what bandwidth that model is accurate. So you can see, you know, it starts to become inaccurate around 30 kilohertz or so. And it's also inaccurate below 100 hertz because you start leaking into the control domain of the droop control. Which will affect the impedance measurement as well. But this is the type of thing that, you know, you can use for some small signal transient dynamics. You can develop an equivalent circuit model for a variety of different inverter topologies. You could do it for grid tied or grid following inverters that might have an open circuit model that looks more like a current source. It should be very flexible for different types of inverters. Now, I should make a clarification point here that this is all going to be small signal modeling. And we would want to be very careful to educate the industry if we provide data like this from an inverter, that this should not be used for short circuit analysis. Inverters, and I don't really talk about this at all in this presentation, but inverters obviously are going to have a very different short circuit characteristic than a generator would. And if you were to use this impedance model to do short circuit analysis, you get some very wrong results because the inverter has to implement high speed limiting just because of the way it's designed, it's digitally controlled. So we would need to develop a whole different framework for modeling that as well. It's got a nice framework for implementing system controllers in the same domain. So with a system controller, you're no longer controlling active reactive currents directly. You're monitoring them by monitoring the current flows through a tie line, and you're using feedback to try to correct them using secondary controls. And in this case, because we come up with a generalized governing response, which has an active and reactive current response to both voltage and frequency, we need an equivalent generalized calculation of area control errors, where we have an area control error in both voltage and frequency domain. And I don't show it here, but you could also do something for both, calculate area control errors for both positive and negative sequences separately as well. So this really is not that much different to the way utilities operate control flows today. It's really just a generalized form, because now that we have a penetration of resources that are actually localized to the system, we can use distributed resources to control voltage as well. So in my mind, this is really just a generalized intertie schedule. This is a generalized tie line bias. And we feed in secondary biases from an upstream controller in the same way we would otherwise. So this feeds into a nested control hierarchy, just like we have today, except now we're saying now resources can go much lower into the distribution system. There may be more layers into that control hierarchy, but the principles of operation can operate much the same way, where we have a series of resources that implement some type of governing response and have a primary and secondary and tertiary control API. We might have a local controller localized to each individual home that's implementing tie line bias control localized to the point of common coupling for the home. We might have microgrid operators that are operating at a substation or even a transformer level that are aggregating multiple homes and feeding secondary biases to those homes, and that can continue to work its way up until eventually it just integrates with the automatic generator control that's built into grid operators today. So I mentioned before that one of the requirements, in my opinion, for a simplified approach should be that there needs to be a methodology attached for how it should be used. So here it is. Here is the methodology, or at least one methodology that I think could be employed to configuring these parameters in an inverter that had this type of model. So first is the time constant. In my mind, the time constant should come from simulation, because at least in our experience, the system performs really well when you had the time constant set to its minimum value. You don't actually need inertia in your system for the droop control to be stable. The problem with having a very, very short time constant, though, is that the system, especially if it has, it doesn't have a whole lot of loads that have their own inertia. The system can operate with very, very high DFDTs. The frequencies can change very drastically. And that may not be that big of a deal if your loads can tolerate high DFDTs. But if you have some loads like motors that could be damaged by high-speed DFDTs, you may actually want to slow the inverters down, not for stability reasons, but to make sure that your frequency isn't changing as quickly so you don't damage motors. So in my mind, this would be dictated a lot by simulation and by the type of loads that are attached. I do think that as the system gets larger and larger, this actually becomes less of an issue, because you're going to have a lot of loads in that system that provide inertia themselves. So the inertia, even if your inverters don't have any inertia, your loads can provide that, and they can provide limiting to the DFDT. That coupled with the fact that you start to get a lot of load, you get a lot of load diversity, so there isn't going to be a large step change in your load at any moment in time due to the statistical averaging working in your favor. So this becomes, I think, less and less of an issue as systems get larger and larger. You can actually make the inverters run faster and faster. The resource, the governing matrix of the resource can be set up based on this equation here, where this matrix on the left is actually the rotation matrix that's set based on the X/R ratio of the interties attached to. And this optimizes the voltage regulating response to your system. If you don't know what that is ahead of time, you could just set it to 1. This is a pretty safe setting where it guarantees at least 70% projection of your current response onto the ideal response for voltage regulation in your system. The droop gains KF and KV, that determines the level of participation of your resource. So how much its power, its active current, reactive current will actually change as a function of change in system settings. So if you have an inverter that maybe you don't want to participate at all because it doesn't really have advanced code, it may not even have the code at all to implement this, in which case you would model it with those gains set to 0. It's a non-participating resource. But in other words, you would do this with, I think, some simulation. There's trade-offs between high gains and low gains. In our experience, though, that you should limit these gains to less than Imax over 1 Hertz or Imax over 5% of the VREF voltage, just to make sure that you're not responding too aggressively to tiny fluctuations in voltage and frequency. For small systems that have a single point of common coupling and negligible load governing, you can set the G matrix of your area controller to just the aggregate of all of your resources. So this is a equivalent to tie-line bias. This is like a generalized form of tie-line bias control for small systems. Because in this case, we're saying for individual home where we think 99% of the governing response is going to be coming from the inverters themselves, only a very, very small amount is going to be coming from the loads, then that means that you can actually know that the governing response of that home is going to be based off of the configuration of the inverters themselves. So it's directly calculatable. But as systems get larger and larger, you may not know what the governing response of the whole system is. There may be a large amount of the system that has a governing response that's not determinable, or maybe coming from loads that you don't know what the governing response is. And also you're going to have possibly multiple interties, which means that the G matrix won't be the same everywhere in your control area. And that's going to be a big fundamental difference between this generalized form of tie-line bias control and the one that's used today. In areas today where they're only really controlling power and they're using things like tap changing transformers and cat banks to control voltage, they're not using distributed resources. There's really going to be one governing response for your area, which is going to be a function of net intertie power flow and frequency, which is the same everywhere. Now, voltage is not the same everywhere. So we may actually have to calculate a G matrix that's going to be slightly different at the different interties on a control area. So this would have to be directly measured. And also, it would most likely need to be aggregated differently as well. Today, you calculate a net area control error by calculating a net intertie error and then multiplying that by your tie-line bias, multiplying that by your tie-line bias and adding it to your voltage and frequency, or just your frequency. With a generalized form where we have voltage and frequency in the equation, in my opinion, we should actually calculate the ACE of a control area by netting the ACEs at each intertie. Now, I've never simulated this before. This is an idea that I had where you basically calculate a net ACE based off of summing the area control errors at each intertie. In my mind, I think it would work out that it kind of comes up with a good average voltage regulation. It can't perfectly control the voltage at each point, but I think it would converge to a good net control of voltage. But like I said, I've never actually simulated this. One of the reasons why I'm presenting it here, I'm hoping that someone gets inspired by this presentation and says, oh, that looks like an interesting way to control it in a very simple model. Maybe I can simulate it and see if it works. But this is kind of a lead into the next slide, where I definitely acknowledge that I haven't thought everything through with this model. There are definite rooms for innovation and areas where this system would not perform perfectly. And there are rooms for solutions that we don't have yet. One is, as I mentioned, the voltage regulation strategy. How do we properly leverage these distributed resources to actually regulate voltage throughout the distribution system? Second is inverter settings and impedance interaction. So now that our inverters are programmable, we can actually program this governing response and to some extent like, program the impedance that they can present, or the small signal impedance they can present, you have a bit of a chicken and egg problem, right? Because in my methodology, you said that I mentioned that, you know, we can set the X over R ratio of this matrix to match the impedance at the point of common coupling looking into the rest of the system. But if you have a microgrid that's built out of these configurable inverters, that impedance will actually depend on the configuration itself. So there's, I think, room for innovation here on how to properly optimize that, where you actually have some control over what the impedance will be looking in at various parts of your system. Third, real-time measurements of the G matrix for setting your tie line bias. Like I said, only for small systems would we be able to calculate the G matrix directly. As the systems get larger, there'll be a need for actually making a real-time measurement of this based off of disturbances that are occurring in the grid naturally. So there's definitely room to come up with some DSP there to try to infer those responses without having to introduce a scheduled disturbance in your system. Distributed area control, distributed controls of ACE. Like, is there a way to do this without having centralized controllers on each area? I think this is a data model that leverages itself to different types of architectures, both hierarchically as well as distributed in nature. This fifth one is an issue that we actually have some experience with. We've seen it in the field, is when you use this generalized area control error, it creates a very unique windup issue, because now the inverter, if it hits a limiting on active or reactive current, so let's say you have a solar inverter that hits its maximum power point, or a battery inverter that hits its maximum power capability, then that will cause an area controller to wind up both of its ACE terms, both voltage and frequency. Even though there's only one actual term, either active current or reactive current, that's actually hitting a limit. And this causes the reactive current to become very off schedule. And, you know, Enphase has developed some techniques for addressing this, but it's definitely a room for innovation, is how to do wind up where you have this rotation partway through. That means that you get wind up on both terms, even though one of your input terms is actually limited. 6, adapting to highly dynamic governing response. So what I mean by this is that when you have a high penetration of distributed energy resources, the amount of governing response that you have is going to depend a lot on the conditions, how much sunlight you have, what time of day it is, how much wind there is, the state of charge of your batteries. The governing response of a large grid that is dictated by power plants is, I think, much more predictable, because you're scheduling when these power plants are operating. When you have resources that have energy based off of environmental conditions, it might be more difficult to schedule, and you need to develop an area controller that can cope with those dynamic responses and may have to adapt its tie line bias very quickly. Negative sequence controls, how do we actually properly aggregate this data model so that single phase inverters that are connected to multiple residences can look like a 3-phase inverter at a larger level. This is an area, this is actually an area of ongoing research right now with another project that we're working on with the University of Washington. And then also tertiary control of IA and IR. How do you actually, because there's cross coupling there, right? Most inverters have a limit on the apparent current they can inject. So the more reactive current you inject, the less active current you'll be able to inject, and vice versa. So now you have a cross coupling of your tertiary control system where you need to optimize not just the active current each resource is running at, but the reactive current. So even with a common data model like this, I think there's tons of room to come up with new ideas and to innovate for the manufacturers, and actually, you know, come up with some IP that doesn't have to interfere with having a common framework for doing the control. Joint technology development. So this is an area that some of you are aware I'm very passionate about. In my opinion, the work product that comes out of UNIFI should include some actual software. And that software should be very valuable and useful to the industry. I would be disappointed if we get a lot of, if we just get a new standard and a lot of documentation of that new standard. I would consider that a failure, because now it's really just something else that inverter manufacturers have to support. And you're basically burdening them with developing additional APIs and additional software. I think that this project it's a good opportunity to come up with some actual common libraries and some common softwares, at least some common tools, even if we don't develop the firmware that runs on the actual inverters themselves, maybe we can come up with some common tools for ways to communicate with them properly. But in my idealized world, the technologies would look like this. First, a control library, a library that's very generic, which means it supports single-phase inverters, three-phase inverters, inverters with different topologies, such as voltage source inverters, resonant inverters, multi-levels. Any topology should be able to use this generic library. So it should only exist to the level where it needs to. It doesn't need to go deeper where inverter manufacturers start getting into their secret sauce. It should be free and open source. It's not something that should be charged. I think it should just be licensed MIT or Apache so that it would be easy for anyone to be able to use this in an actual product. It should have exceptional quality, which means that it's well tested, well documented, well reviewed and vetted, and properly marketed as well. And that last part's kind of key. Like, it doesn't matter if there's a really good library and really good software if people aren't aware of its existence. So I think there needs to be a lot of work that would have to be done on marketing it to industry so it actually gets used. It needs to have high performance. Inverter manufacturers aren't going to want to use something that's worse than what they already have. So it should support having a very low memory footprint so it can be used in low-cost processors. It needs to be fast so that it can be used in high-speed controls. It needs to be a well-designed and well-articulated library. It should be very portable, work on a variety of different processors, both with operating systems and without. And that kind of ties into its simplicity, right? It's a simple library. It's one that we can make very portable pretty easily if we're not leveraging resources that are only on certain types of processors. And last, very easy to use and to integrate. And that kind of ties into the high quality where it needs to have excellent documentation and good community support. Second is a flexible and extensible data modeling system with a configuration API that ties into that. And that data model system should support multiple different types of physical layers so that you can use it to communicate with an inverter, interact with that data model over serial, over power line communication, RJ45, CAN bus, Wi-Fi, Zigbee, pretty much anything, you should be able to interact with that data model. And then last is an integrated configuration management system that works hand in hand with that model generation. So the idea is that the inverters are configured with the exact same files that are used to generate models of them so that you know that you're modeling the exact inverter that you configured for actual use in that microgrid. So how would this look? So here I kind of drew a very, very simple kind of flow diagram that showed how some of these tools might work. So first would be the development of a UNIFI schema. And this may be something that already exists, right? There are some schema systems that exist today for defining how data is represented. Probably a very common used example that's already very performant is something called Protobuf, which was developed by Google, which is just a way to describe data. And the idea is that you can develop device models for both APIs and configuration options based off of that schema. And the UNIFI would provide, as part of that, a device model that's built into that schema framework that says, here's how we want to describe our inverters. And it only exists to the level it needs to, right? This would be very, very simple. It really just defines this simple API. But vendors, I think, should be able to build their own proprietary technologies on top of this. So the idea is that inverters may have their own, sort of secret sauce firmware for doing things like advanced maximum power point tracking, maybe something fancy with harmonic compensation or islanding, anything that's proprietary. They should be able to build off of the same schema system so that they can configure their inverters using that same framework. So it should be extensible. It should have a configuration system for defining what the values of these in non-volatile memory are when the inverter first starts up. So these are the configuration files that define how that inverter is programmed. So those configuration files would combine with the unified device model to generate model files in some sort of standard framework that is used by microgrid developers and utilities that they can use to actually simulate those inverters. And then as part of this, there'd also be a cogen that doesn't actually develop the application code, because like I said, it'd be up to the inverter manufacturer to figure out how they want to enforce this phasor relationship. Either they use, virtual oscillator control, droop control with a PLL, or some other type of control I haven't heard of. As long as it has this relationship, they can develop the application code, but the unified code generation tool could develop the header files that are used to describe how, the configuration of those libraries. And then you would have on the right the actual source code for your target. So with this system, we actually support something called schema-based messaging. So this is schema-based messaging is something that's starting to gain a lot of traction in industries that require a lot of performance or require support of very lightweight processors. The idea is that the classic way to communicate with devices today is something called REST, right? Where you're sending these, you're basically sending JSON files to a target, and then you have a specific API defined for how you actually send that file. So schema-based messaging says that you don't actually define the structure of your data in the message itself. The structure of your data is defined someplace else. And that you have a tool for basically serializing a message into a lightweight binary only readable data format. And as long as you have the same schema on each side, that message can be deserialized by the target very efficiently. So which means that you can implement this interface on extremely low cost, lightweight processors. It provides a little bit of additional security because now the only devices that can communicate with your target are devices that actually know what the data model is. So you can do some verification there. And it's very extensible because now if you want to change the way that you communicate with a target, you're not having to write a new document said, oh, by the way, we're adding these messages onto the REST API. You have to make sure that your target is able to now parse these messages out of that JSON file that will be written like this. With a schema-based messaging system, all you do is define a new model. And as soon as you define that new model, you can extend the framework very easily because like I said, the header files are automatically generated with this technique. So there's very little extra work you have to do on either the send side or the receive side to extend that model in the future. So the way that works today is your gateway basically just sends a message to your target saying, what are your data model hashes? That target responds back with the hashes of the model it's using because it may be one that supports a legacy version of a model. So let's say we update the model in 2024. We may have inverters in the field that were built in 2022 that use old data models. That's okay, because we still know how to communicate with those. We can see the hash, we can look up a data model in a database, we get the schemas back. Once we have those schemas, we know exactly how to communicate with that target. We know how to serialize the data, and we know what the deserialized data that the target sends back will look like so that we can communicate very efficiently, very robustly in a very future-proof way. So Enphase has developed its own technique for doing this, but there are some open source techniques as well. Probably the most common is something called gRPC. It was developed by Google as well. It's built on top of protobuf. So the idea is define your messaging format with .proto schema files. You define your data models that way. And then once you have your data models defined, your API can use gRPC to send that serialized data back and forth. So, but what about getting from here to there, right? Like 2030.5, I'm not proposing that we just delete 2030.5 in favor of this new system and do everything this way. There's going to be, I think, a middle ground where inverters that might want to be starting to support a new framework still have to support legacy system controllers and gateways. And in my mind, the reference implementation for those should be actually provided part of the UNIFI tool framework as well, where we have a reference implementation of like a 2030.5 server or an ADR or some custom type of communication library that a utility needs support for. And then that interfaces with a protocol library that's able to translate those messages into either secondary control action or configuration options if it's an autonomous response directly to the inverters that gets relayed over a vendor bridge that communicates that data using the lightweight schema-based messaging now over some type of PHY of their choice. So I got permission from Enphase to show some eye candy here about some of the tools that we've developed that we're actually considering open sourcing. So Enphase is in the early stages of developing an open source committee and an official open source policy for determining what actual tools that we decide to make public and to try to endorse as a way to do things, and to kind of get a feel for the appetite there is that in the industry, whether or not there are, other possible even competitors that might be interested in collaborating, how useful these tools would be to microgrid operators. I got permission to show at a high level how some of these systems work. So I'm going to give a little bit of, I wouldn't say demonstration, these are just slides, but a little bit of code showing how we do certain things today, both with our data model system, which we call EDMS, End-Phase Data Model System, and our control, debug, and configuration protocol. That's basically how we serialize that data and communicate with our inverters, which we call ECDC, which stands for End-Phase Control and Debug, End-Phase Control, Debug, and Configuration. So we use an XML schema file. So XML is a language that lets you actually define your own schema. It's used to verify whether or not you're describing data correctly. We actually built this. It's very, very similar to protobuf. We really built this before the existence of nano PV, which is a lightweight version of protobuf that can run on microcontrollers. We designed this because that didn't exist yet, and we needed a lightweight schema system and communication protocol that did work on lightweight microcontrollers that we had on our inverters. So we defined our own schema file, which it really just defines how you describe data. And this is a short example of how we can define part of the SUNSPEC data model, right? So SUNSPEC is a pretty well-known data model. It's well published. It has a variety of different controls and configuration options for different inverter functions. And here I showed how one part of that, particularly the power factor control configuration, could be actually described in a generic data model framework, which means you wouldn't need to actually publish the data models. You wouldn't have to publish like how the data looks itself. You can just create this data model file. And then if you have a framework of tools around this, it makes it very easy for the manufacturers to implement because they can automatically generate header files and model files from these data models. So here shows how you might define a UNIFI model. So this is actually a version, and I didn't put the units in here for brevity, but this shows how you might describe the data model definition for a UNIFI API, or in this particular, this would be a single phase API for both the primary control configuration as well as the secondary and tertiary control APIs. For how you actually communicate those. So with these data models, you can actually create some very powerful Python libraries for interfacing with some of these APIs. This shows the API for our scope function. So all of our inverters have basically a built-in digital oscilloscope, which lets you capture internal data in any part of the data model itself. So anything that's in your data model that's described can be captured using the scope framework. And I literally captured this one this morning just for this presentation to show you the power of this. So you can, once you establish it connecting with an inverter, we have this scope abstraction that lets you set the channel. So you just point it to part of your data model. So in this case, I'm setting 4 channels in the scope, PCU data model telemetry, V out, I out, V in, and I in. So I'm trying to record the input voltage, the output current, the input voltage, and so output voltage, output current, input voltage, input current. I set a trigger. We have triggers for rising edge, falling edge, rising or falling edge, on equal to, immediate. We have basically all the different types of events that you can have on a scope as well. You can define a post-sample trigger percentage so that you can trigger at either the front or the back, and you can capture it. And the beauty here is that it's able to operate very efficiently on some very, very lightweight processors, as well as very low bandwidth communication systems, because all the data is actually serialized and deserialized using a schema that's known ahead of time. We're not sending any information about the schema as part of this translation, so that you're able to do these types of captures on very, very lightweight networks. And then once you get that data back, the system will automatically parse it, and it will, even though the underlying data itself is all going to be in a fixed point. Actually, I think all this data was actually 16-bit, wasn't even 32-bit. Because the data has the schema file, it's able to convert that into a floating point number that's easy to plot, right? So gone are the days of doing a manual capture on something like TerraTerm and then capturing a giant hexadecimal buffer, copying and pasting that into Excel and trying to post-process it, right? With schema-based communication, the schema knows how to interpret that data for you, and present it in something that's a human readable form. Here's a simple secondary and tertiary control API that can work on top of this data model. So here I'm defining a connection to a gateway. I'm setting a group ID for different types of inverters so that I can use a multicasting that a PHY may support. So something like PLC, a lot of places have the ability to broadcast or multicast a single message that doesn't get a reply that multiple systems respond to. Our Powerline Com is one of them. So we can set different group IDs as well as an alias that lets us address them by name. And then we can broadcast secondary and tertiary control messages to those group areas. Okay, I think I'm about on time. I told Duncan about 40 minutes. I think I finished just in time. So yeah, thanks everyone for listening to my presentation.